Hey YouTube, and welcome back. Today's video, as promised, we are going to look at how to drive and run three-phase electrical equipment in your shop at home. Stuff you might have bought on an auction site, gotten a deal from the shop down the road that's closing down. We're going to look at that. We're going to look at a little bit of the fundamentals behind it. I'll go ahead and make an apology ahead of time for the microphone. I did do a couple funky things, but I thought the content was good. We're going to stick with it. So stick through that 15 minutes-ish of quote-unquote theory, and we'll come back out to the shop here in a little bit and actually look at my drill press. All right, so I'm going to scoot around my little whiteboard session here. I'm going to redub this audio. Hopefully it is better than what my original microphone was picking up. It was very high-pitched, hard to listen to. We're going to start off here by talking about what we can expect at our residence, right? Our homes. In North America, the typical home is receiving electricity at the standard 60 hertz, right? That's how it gets generated from the utilities, the power generation stations, and transmitted to our house. Now that is what is called single phase. I get asked the question all the time. Hey, I have a black wire and a red wire coming into my house. Is that two-phase? And that is all considered single-phase power. I am going to oversimplify this, but that is the case, right? So most houses in the continental U.S. have 200 amp services. You may have an older home or live on a farm or homestead that may only have 100 or 60, but generally speaking, you'll have a 200 amp service. If it's a very large home, it might be a 400 amp, but at the end of the day, it's still this 120, 240 volt, single phase power system. And this is something I consider myself an expert on. I've spent my entire life in the electrical industry after graduating high school. I spent the last 15 years specifically in industrial automation, focusing on variable frequency drives. So I do know a thing or two. And that is all, like I said, single phase. That's how the whole market considers it. If we look at industrial then, and this is, the biggest user of three-phase power, what industrial operates on are a number of different voltages, and it really depends where they're located, their geographical location with regards to different power plants, but they're either going to be 120, 208, they're going to be 120, 240, and I know that one confuses people a lot because people will be like, well, that's the same voltage I have running to my house. Yes and no, and we'll look at that in a minute. And then 277, 480 is really the last big common one. And this is where, you're going to have three wires coming into that service. You're going to have a black, a red, and a blue. You're going to have a brown, orange, and a yellow. And, that's kind of three-phase power in a nutshell. Now, I'm going to oversimplify this 180,000 foot view, but it's enough to give you kind of a basic understanding. Likewise with motors, when we look at an industrial motor, there are I'll say two kinds of industrial three-phase motors. There's a fixed voltage motor, or there's a high-low voltage motor. Okay, most of what you'll probably find on equipment are going to operate. They're going to have a wiring diagram in there, so you can wire the motor for low voltage, and you can wire it for high voltage. Now, what that means is in a low voltage setting, that motor could be rewired inside the pecker head on the side of the motor, also called the motor termination box. It's where all the leads of the motor come out to and connect to your building wire. In that motor, you'll see 9 leads. And you can wire them one way to be able to run on 120, 208, or 120, 240. You can wire them another way to run on 480 volts. So they're either running on 208/240, or they're going to run on 480 volts. So if we look at the diagram up here, in low voltage mode, T4, T5, and T6 would get, we'll say, Wagoed together. I don't like people using wire nuts, specifically with motors that aren't used to using them. There's a ton of room for error in there. Wagles are the little clip connectors. You flip open the clips, put the wire in, and then snap them back shut. They work very well. I know quote-unquote experts in the trades will hate them, but I can honestly tell you I've had more wire nuts fail than Wagos, and to date I haven't actually had a Wago fail that when it was used properly. So, off my soapbox here, if we look at that low voltage example, then we're taking the wires, and these wires will typically have a label on them, like they'll have a little printed text on the side of the wire, and sometimes you have to put your cheaters on to see it, but trust me, it's there. Or they'll have a label, sometimes a physical label, but we'll take T1 to T7, and then we'll take the first wire from our drive or from our phase converter. We'll repeat that process for T2, T8, second wire, and then T3, T9, and then the third wire. And you can see that wiring actually changes when we go to high voltage. And all that's happening there is it's connecting the copper windings inside the motor in a different orientation to let that run on different voltages. That is the long and short of that. Let's skip ahead here. So here you can kind of see we are now looking at a basic, we'll say, what I'll call a single phase variable frequency drive circuit. And there are whole college classes that you can take entire semesters learning this in the theory and the programming and operation. And this is not the platform for that. But I've modified this to show a single phase drive. This one is showing a 240 volt single phase input. So if you see, we'll look at it here, but the front of the drive, that's where your 240 volt single phase. So if you're coming off a breaker, you'll have a red wire and a black wire typically. That's where those get put in. And if we skip ahead here a little bit, that's really the front half of the drive. And what you see the box on now is what I'd call the back half of the drive. So if we pause here and just take a look at this on the front half of the drive, here is where there are diodes in there. Again, a diode, think about it, it chops a waveform in half and sends part of the voltage one way and none of the voltage the other way. So you have opposing diodes in here that create a DC bus. So you're taking AC power in, and much like the charger for your laptop or really any electronic device that you plug into an AC power outlet that runs on DC, this is what it's doing. There's diodes of different styles and kinds and varieties that are taking that AC waveform, creating a DC pulse and kind of charging through a capacitor for storage and creating this DC bus that runs across this variable frequency drive, really all drives. This is an example of a 6-pulse drive. It's probably the most common drive in the market. 97% of drives you're going to find are going to be what they call 6-pulse. And where that comes in is on the back side of the drive. Skip ahead here. There we go. So the back half of this drive, they call it 6 pulses because they have 6 electrical components called IGBTs. And what those are doing is they're computer-controlled switches in its most general statement, and, making this 180,000 foot view. And what's happening is the computer inside the drive is telling that to turn on so fast per second and for so long per second. So it's going to stay on and off for a set amount of time. It's also turning on and off so many cycles per second. And that's what's giving us our variable frequency. Okay. I mentioned at the beginning that power that's generated comes in at 60 hertz. And when we talk varying the speed of a motor, there's only so many ways you can do that. I'm not going to get into Ohm's law, but if you feel like it, go Google Ohm's law. Again, there's entire books dedicated to it. But adjusting frequency is one of the ways that we can run a motor. So every motor has a base speed, right? We're going to see motors with typically 3,600, 1,800, or 1,200 RPM base speed motors. That means when power comes in at 60 hertz, that motor can run at that speed minus the slip speed, which again doesn't much matter for this conversation. But generally speaking, right, you have 1,800 RPM, 1,200 RPM, 3,600 RPM. The motor's trying to run at that speed based on 60 hertz. So what this does is by taking these 6 IGBTs here and turning them on and off and keeping them on and off for different times, it's actually adjusting the output frequency. And it's also adding our third power leg. So it's creating kind of a new 3-phase service on the backside of the drive. So we're feeding this with 240 volts single phase in this example. It's charging a bus that's probably running somewhere between 350 and 380 volts DC. Then it's taking that DC power, chopping it back up and creating what they call a modified sine wave. It's a square sine wave, but to the motor, it looks good enough to spin a 3-phase motor and control it. Okay, and that's what it's doing on the back half of this. And you'll see these 3 connection points, typically called T1, T2, T3 on the drive. That's the motor termination points, and we'll go look at that on an example. I don't think there's anything else I wanted to specifically cover here. This is pretty common and pretty standard. So we will scoot ahead here a little bit. And the next technology we're going to look at is going to be what they call a rotary phase converter. So this is a little bit different of a beast. Again, I'm going to oversimplify this, but you can kind of think of it as getting a motor to run with only 2 wires of a 3-phase system. But then once the motor's up and spinning, using that third terminal to create a 3-phase output. I know that probably didn't make a lot of sense, but what they're basically doing is you can run a 3-phase motor on 2 phases. The trick is you have to get a rotational magnetic field in a 3-phase motor for the shaft of the motor to spin. And that's kind of what a rotary phase converter is doing in essence. It's using a single phase input. It's grabbing a third leg, or sometimes it actually has a starting motor. It really depends on the brand. I know these have come quite a long ways, but honestly, the ones that the average Joe is going to afford out on Facebook Marketplace or eBay is going to be the old style, and that's probably going to be a 2-motor type of solution. But basically, the first motor gets the second motor started, then there's a contactor that drops out the starting motor, and then that other quote-unquote motor is kind of being used as a generator of sorts to then give someone 3-phase power. Now, this 3-phase power, I will say, is a lot cleaner, right? So if you're going to run a machine with control wiring or a separate control power transformer that's going to run, I don't know, a little computer or sensors or anything like that, this is probably the way you want to go. The variable frequency option is very nice for things like I'll call simple applications, right? Like screw compressors, drill presses, milling machines. What's another example of something might be there? Big grinders, I guess, or polishing pad machines. If you're in the woodworking, maybe like big jointers, big planers, things like that. Whereas if you're going to try to run some type of, I don't know, XY axis type industrial machine that has other controls on it, rotary phase converters might be the way to go, but I'll say that's going to be the exception, not the rule. All right, I think that's all I wanted to touch on here. Again, we'll go out, we'll look at a drive, go through that, and then go take a look at the actual drill press that I own. So now that we just went through a little bit of whiteboard and what I'll call motor and drive theory, let's take a look at an actual variable frequency drive. This one happens to be an Allen Bradley PowerFlex 4. It's a fairly old drive, but a lot of times they still work just fine, and there's probably a decent amount of these on places like auction sites and eBay. So typically when you open up a drive, come back here, you'll have a front cover, and again, this will typically have a little bit of information about what the terminal blocks do. There'll be typically a finger safe cover that you can remove then to gain access to the power terminals. Now, assuming you bought the right drive and you bought a single phase input drive, typically those will have terminals. Here in North America, we're pretty used to L1 and L2. So that would be like your black and red wire you might have feeding this drive from like a 20 amp breaker. Don't worry about BR. Those are for if you have to stop fast. A whole bunch of drive theory later. BR stands for braking resistor. You typically won't have to worry about those in this application. And then you have your motor output. So you can see we have single phase input, but your motor still has 3 terminals, 3 phase output. So you have T1, T2, and T3. Those 3 wires will go to your motor terminating box and be joined with whatever other wiring that motor requires to run low voltage. Now, we didn't talk a lot about grounding, but grounding is very important when it comes to drives. Okay. Now, the way I would do this is the first ground terminal comes from your panel or from wherever you're feeding this drive from. The second one, I would say, would go out to your motor. That would be the ground that goes along with your wires out to your motor. If we look at the side of this drive, kind of pulls up some specs, we can see that this is an input, right? Single phase. We can feed this drive with 200 to 240 volts, which is perfect for panels here in North America. And the other important thing here is the amps. We really don't care about horsepower necessarily as much as amps. So we want to make sure that however many amps our motor drives when wired to low voltage, okay, that this drive is at least meeting that requirement. I'd prefer the drive to have more amps available to it than the motor requires. And other important information here, that should be really about it, okay? The other thing that I want to take a second and talk about with these is control. Now, I'm not going to go into all the different ways that you can wire inputs and outputs to this to start or stop. I'm also not going to talk about programming because every drive programs differently. Most of these manuals are available online. You can finagle your way through these buttons and program it just fine. Some of these have free programming software like the Allen Bradleys do. Theirs is called Connected Components Workbench. And you can download that for free if you want to program these using a computer. Likewise, there's all sorts of things you can do. You can wire up a stop button, a start button. You can wire up like a speed pot if you want to, vary speed without having to use the buttons on the front of the drive. And if I did a video about that, this would be like a 17-part, 47-hour video, and that wasn't really my intention with this necessarily. So that's looking at this physical drive. Now, finally, after all that, let's go out and I'm going to try to shimmy behind my drill press so we can take a look at that. Now, I will apologize ahead of time. Some of this may be a little hard to see. And this drill press table weighs about 1,200 pounds. So I'm not going to move it, but I will try to squeeze back there. We'll look at the motor nameplate, look at a few things I've added on here, and we can talk about it. So this is my Rockwell Delta 20-inch drill press. Exceptionally heavy, exceptionally powerful. It's been a very good unit. I got this for a song. I think I paid like 380 bucks. And the guy even dropped it off at my house. Granted, I needed a skid steer to move it in here, but that's the model of it. I always forget the year on this, but so we climb around here and look at the motor that came on this. We'll try to get a shot of that. This one actually has an example where the wiring diagram is on the nameplate, and we'll find things here like horsepower, RPM, and the voltage range. Now, obviously, I have this one running. This is capable of both 480 and 208 three-phase. And again, I believe inside this cover is another diagram as well. Actually, this one is in 2 spots. So what I did is simply took some unistrut, drilled and tapped the base here just to mount this cabinet. I had this laying around. As you can see, it doesn't really fit well in here, but I don't use it long enough where it gets too hot. But you can kind of see in there I got, you know, a bunch of extra cable on the bottom. I had to mount the drive on there sideways to be able to fit it. But really, this box is just for protection. Keeps the metal dust out of it. Metal shavings, things like that are not good for drives. So you want to protect it. Again, that box I had laying around. Now, I'm generally, like I said, sometimes I'm in a rush and I don't think about things. Kind of an idiot that way. So here is just a quick Amazon special push button. And I put it there so when I'm drilling, right, typically that's where my leg is. So if I do get caught up, I just have to move my leg forward. And I can hit that stop button with my leg. I have that stop button wired in with this one. And it's fairly simple. You open this up. This is just a start-stop button. I ran some of my own wire inside the drill press here, opened up the cover, and ran that back to the drive. I have a digital readout that's started up here. I'm not done with that, but these 2 wires also go into this box and then down to the drive. This is one I added. This one actually came on the drill press. This actually, I gutted it. This had a starter to run that when you're connected to 480 volts. But here you can see this is like an Eaton or something disconnect switch. But when I turn that, I have a stack light coming up here. That just green means, well, one, the drive is not faulted. The drive is ready to run. And I have a speed control up here. It's not marked, but I know for most metals, call that 10 o'clock. It's pretty good to go. This one down here does my forward and reverse. Again, you don't have to wire all this, but most of the drives you buy out there will have terminals for start, stop, reverse, speed control, like this speed pot here. So this does my forward, reverse. Let's see, is there anything else on this? I think that's about it. I did make sure I went through and regrounded everything, right? Again, like I said before, grounding is important. So I made sure the cast iron case was grounded. I made sure that was grounded to that okay. That this in here is grounded to the door. So the way this works is power comes from that outlet to the disconnect, and then this feeds the drive in that box. And again, you can find all this on eBay, Amazon. Shouldn't be too hard. But now when I start this, oh yeah, that's right. This actually has an issue at the moment. Please hold. All right. So, like I said, real guy, real shop, this kind of thing happens. But I was able to get this troubleshot. I troubleshooted it. I fixed it. I fixed it. Again, it's a mess in there. Don't look at that. I'm only a professional when I have to be. At home, I just make things work because sometimes that's all the time a guy has in a day. But now, right, so green light, good. What was happening is this plate shifted and the button wasn't buttoning. It wasn't pushing the plunger for the switch in. But now you can see that we have a spinning motor. And I will say, you know, this might be something like 5 hertz, right? So that drive is modulating. It's chopping up the voltage, using that to, in a way, change the frequency on the output of the drive. As we turn the switch up to say something like 30 Hertz, typically I'll probably run about 20. 20 seems to do pretty good for cutting metal. I have the belts pretty much wired at motor base speed. So this is an 1800 RPM motor. I wanted to make sure, as far as torque management wise, I'm kind of just, I picked a standard. So I picked base speed of the motor, 1800 RPM. That's the middle of each pulley. You could play around with these belts if you had to get more torque out of the unit. But typically, if you start exceeding the machine torque here, that belt's going to start slipping because a drive is capable of producing full torque typically at any given speed, right? Oversimplification, but generally speaking. But that's how I have mine set up on this particular unit. But if you're going to do some higher speed stuff, I mean, yeah, go ahead, crank this thing all the way up to 60 Hertz. Like I said, it's nice. I'm not having to swap belts around every time I'm changing material or anything like that. I have done some tapping with this machine as well, and some 3-core drilling. So there are times where I do want to vary the speed, maybe even while I'm drilling in material. Kind of some two-handed operation there. But then again, right, like I could hit the stop down here, hit the stop here. They both cause the drill press to stop. So that's my 3-phase Rockwell Delta massive drill press. But again, I will venture a guess you could buy all these parts used if you're thrifty enough to do this type of conversion, right? Including the price, like if you had to put a breaker in that panel, I don't know, we'll say $350, $400. And for me, that was worth having a nice drill press with a big table, where I can pretty much, you know, stick a 1-inch drill bit in that if I had to, and I don't know, put a big hole in thick metal, I guess. Hey, again, thanks for watching. I do apologize for the microphone before. Again, I'm still figuring this out, so bear with the guy. Maybe if I do more screen capturing in the future, I'll look at putting out one of those big headsets or getting an external mic. But again, please hit like and subscribe if you like what you're seeing. If you have any questions, feel free to put them in the comments below. I will put some links to different products. I'll put some examples of drives that I find on eBay maybe for you to go out and look at. And again, proceed at your own risk, but it's certainly doable to power this type of equipment with a used variable frequency drive and do it in a economical-ish fashion. Until next time, thanks for watching Beyond the Manual.